Milling is the machining process of using rotary cutters to remove material from a workpiece by advancing in a direction at an angle with the axis of the tool. It covers a wide variety of different operations and machines, on scales from small individual parts to large, heavy-duty gang milling operations. It is one of the most commonly used processes in industry and machine shops today for machining parts to precise sizes and shapes. Milling can be done with a wide range of machine tools. The original class of machine tools for milling was the milling machine. After the advent of computer numerical control, milling machines evolved into machining centers, generally classified as vertical machining centers and horizontal machining centers. The integration of milling into turning environments and of turning into milling environments began with live tooling for lathes, and the occasional use of mills for turning operations led to a new class of machine tools, multitasking machines, which are purpose-built to provide for a default machining strategy of using any combination of milling and turning within the same work envelope. Process. Milling is a cutting process that uses a milling cutter to remove material from the surface of a workpiece. The milling cutter is a rotary cutting tool, often with multiple cutting points, as opposed to drilling, where the tool is advanced along its rotation axis. The cutter in milling is usually moved perpendicular to its axis so that cutting occurs on the circumference of the cutter. As the milling cutter enters the workpiece, the cutting edges of the tool repeatedly cut into and exit from the material, shaving off chips from the workpiece with each pass. The cutting action is shear deformation. Material is pushed off the workpiece in tiny clumps that hang together to a greater or lesser extent to form chips. This makes metal cutting somewhat different from slicing softer materials with a blade. The milling process removes material by performing many separate, small cuts. This is accomplished by using a cutter with many teeth, spinning the cutter at high speed, or advancing the material through the cutter slowly. Most often it is some combination of these three approaches. The speeds and feeds used are varied to suit a combination of variables. The speed at which the piece advances through the cutter is called feed rate, or just feed. It is most often measured in length of material per full revolution of the cutter. There are two major classes of milling process. In face milling, the cutting action occurs primarily at the end corners of the milling cutter. Face milling is used to cut flat surfaces into the workpiece, or to cut flat-bottomed cavities. In peripheral milling, the cutting action occurs primarily along the circumference of the cutter, so that the cross-section of the milled surface ends up receiving the shape of the cutter. In this case, the blades of the cutter can be seen as scooping out material from the workpiece. Peripheral milling is well suited to the cutting of deep slots, threads, and gear teeth. Milling cutters. Many different types of cutting tools are used in the milling process. Milling cutters such as end mills may have cutting surfaces across their entire end surface, so that they can be drilled into the workpiece. Milling cutters may also have extended cutting surfaces on the sides to allow for peripheral milling. Tools optimized for face milling tend to have only small cutters at their end corners. The cutting surfaces of a milling cutter are generally made of a hard and temperature-resistant material, so that they wear slowly. A low-cost cutter may have surfaces made of high-speed steel. More expensive but slower-wearing materials include cemented carbide. Thin film coatings may be applied to decrease friction or further increase hardness. They are cutting tools typically used in milling machines or machining centers to perform milling operations. They remove material by the movement within the machine or directly from the cutter's shape. As material passes through the cutting area of a milling machine, the blades of the cutter take swarm sloughs of material at regular intervals. Surfaces cut by the side of the cutter therefore always contain regular ridges. The distance between ridges and the height of the ridges depend on the feed rate, number of cutting surfaces, the cutter diameter. With a narrow cutter and rapid feed rate, these revolution ridges can be significant variations in the surface finish. The face milling process can in principle produce very flat surfaces. However, in practice the result always shows visible trochoidal marks following the motion of points on the cutter's end face. These revolution marks give the characteristic finish of a face-milled surface. Revolution marks can have significant roughness depending on factors such as flatness of the cutter's end face and the degree of perpendicularity between the cutter's rotation axis and feed direction. Often a final pass with a slow feed rate is used to improve the surface finish after the bulk of the material has been removed. In a precise face milling operation, the revolution marks will only be microscopic scratches due to imperfections in the cutting edge. Gang milling. Gang milling refers to the use of two or more milling cutters mounted on the same arbor in a horizontal milling setup. All of the cutters may perform the same type of operation, or each cutter may perform a different type of operation. For example, if several workpieces need a slot, a flat surface, and an angular groove, a good method to cut these would be gang milling. All the completed workpieces would be the same, and milling time per piece would be minimized. Gang milling was especially important before the CNC era, because for duplicate part production, it was a substantial efficiency improvement over manual milling one feature at an operation, then changing machines to cut the next op. Today, CNC mills with automatic tool change and 4 or 5-axis control obviate gang milling practice to a large extent. Equipment. Milling is performed with a milling cutter in various forms, held in a collet of similar which, in turn, is held in the spindle of a milling machine. Types and nomenclature. Mill orientation is the primary classification for milling machines. The two basic configurations are vertical and horizontal. However, there are alternative classifications according to method of control, size, purpose and power source. Mill orientation. Watch video. Vertical mill. In the vertical mill, the spindle axis is vertically oriented. Milling cutters are held in the spindle and rotate on its axis. The spindle can generally be extended, allowing plunge cuts and drilling. There are two subcategories of vertical mills, the bed mill and the turret mill. A turret mill has a stationary spindle and the table is moved both perpendicular and parallel to the spindle axis to accomplish cutting. The most common example of this type is the Bridgeport, described below. Turret mills often have a quill which allows the milling cutter to be raised and lowered in a manner similar to a drill press. This type of machine provides two methods of cutting in the vertical direction, by raising or lowering the quill, and by moving the knee. In the bed mill, however, the table moves only perpendicular to the spindle's axis, while the spindle itself moves parallel to its own axis. Turret mills are generally considered by some to be more versatile of the two designs. However, turret mills are only practical as long as the machine remains relatively small. As machine size increases, moving the knee up and down requires considerable effort and it also becomes difficult to reach the quill feed handle. Therefore, larger milling machines are usually of the bed type. A third type also exists, a lighter machine, called a mill drill, which is a close relative of the vertical mill and quite popular with hobbyists. A mill drill is similar in basic configuration to a small drill press but equipped with an XY table. They also typically use more powerful motors than a comparably sized drill press, with potentiometer-controlled speed, and generally have more heavy-duty spindle bearings than a drill press to deal with the lateral loading on the spindle that is created by a milling operation. A mill drill also typically raises and lowers the entire head, including motor, often on a dovetailed vertical, where a drill press motor remains stationary, while the arbor raises and lowers within a driving collar. Other differences that separate a mill drill from a drill press may be a fine-tuning adjustment for the Z-axis, a more precise depth stop, the capability to lock the X, Y, Z axis, and often a system of tilting the head of the entire vertical column and powerhead assembly to allow angled cutting. Aside from size and precision, the principal difference between these hobby-type machines and larger true vertical mills is that the XY table is at a fixed elevation. The Z-axis is controlled in basically the same fashion as drill press, where a larger vertical knee mill has a vertically fixed milling head, and changes the XY table elevation. As well, a mill drill often uses a standard drill press type Jacob's chuck, rather than an internally tapered arbor that accepts collets. These are frequently of lower quality than other types of machines, but still fill the hobby role well because they tend to be benchtop machines with small footprints and modest price tags. Horizontal mill. The horizontal mill has the same sort, but the cutters are mounted on a horizontal arbor across the table. Many horizontal mills also feature a built-in rotary table that allows milling at various angles. This feature is called the universal table. While hand mills and the other types of tools available to a vertical mill may be used in a horizontal mill, the real advantage lies in arbor-mounted cutters, called side and face mills, which have a cross-section rather like a circular saw, but are generally wider and smaller in diameter, because the cutters have good support from the arbor and have a larger cross-sectional area than an end mill. Quite heavy cuts can be taken, enabling rapid material removal rates. These are used to mill grooves and slots. Plain mills are used to shape flat surfaces. Several cutters may be ganged together on the arbor to mill a complex shape of slots and planes. Special cutters can also cut grooves, bevels, radii, or indeed any section desired. These specialty cutters tend to be expensive. Simplex mills have one spindle, and duplex mills have two. It is also easier to cut gears on a horizontal mill. Some horizontal milling machines are equipped with a power takeoff provision on the table. This allows the table feed to be synchronized to a rotary fixture, enabling the milling of spiral features such as hypoid gears. Comparative merits. The choice between vertical and horizontal spindle orientation in milling machine design usually hinges on the shape and size of a workpiece and the number of sides of the workpiece that require machining. Work in which the spindle's axial movement is normal to one plane, with an end mill as the cutter, lends itself to a vertical mill, where the operator can stand before the machine and have easy access to the cutting action by looking down upon it. Thus, vertical mills are most favored for desinking work. Heavier and longer workpieces lend themselves to placement on the table of a horizontal mill. Prior to numerical control, horizontal milling machines evolved first because they evolved by putting milling tables under lathe-like headstocks. Vertical mills appeared in subsequent decades, and accessories in the form of add-on heads to change horizontal mills to vertical mills have been commonly used. Even in the CNC era, a heavy workpiece needing machining on multiple sides lends itself to a horizontal machining center, while desinking lends itself to a vertical one. Alternative classifications. In addition to horizontal versus vertical, other distinctions are also important. Variance bed mill. This refers to any milling machine where the spindle is on a pendant that moves up and down to move the cutter into the work, while the table sits on a stout bed that rests on the floor. These are generally more rigid than an e-mill. Gantry mills can be included in the sped mill category. Box mill or column mill, very basic hobbyist bench-mounted milling machines that feature a head riding up and down on a column or box way. C-frame mill, these are larger, industrial production mills. They feature an E and fixed spindle head that is only mobile vertically. They are typically much more powerful than a turret mill, featuring a separate hydraulic motor for integral hydraulic power feeds in all directions, and a 20 to 50 horsepower motor. Backlash eliminators are almost always standard equipment. They use large MTB40 or 50 tooling. The tables on C-frame mills are usually 18 inches by 68 inches or larger, to allow multiple parts to be machined at the same time. Floor mill, these have a row of rotary tables, and a horizontal pendant spindle mounted on a set of tracks that runs parallel to the table row. These mills have predominantly been converted to CNC, but some can still be found under manual control. The spindle carriage moves to each individual table, performs the machining operations, and moves to the next table while the previous table is being set up for the next operation. Unlike other mills, floor mills have movable floor units. A crane drops massive rotary tables, XY tables, etc., into position for machining, allowing large and complex custom milling operations. Gantry mill, the milling head rides over two rails which lie at each side of the work surface. Horizontal boring mill, large, accurate bed horizontal mills that incorporate many features from various machine tools. They are predominantly used to create large manufacturing jigs, or to modify large, high-precision parts. They have a spindle stroke of several feet, and many are equipped with a tailstock to perform very long boring operations without losing accuracy as the bore increases in depth. A typical bed has X and Y travel, and is between 3 and 4 feet square with a rotary table or a larger rectangle without a table. The pendant usually provides between 4 and 8 feet of vertical movement. Some mills have a large integral facing head. Right-angle rotary tables and vertical milling attachments are available for further flexibility. Jig bore are vertical mills that are built to bore holes, and very light slot-to-face milling. They are typically bed mills with a long spindle throw. The beds are more accurate, and the hand wheels are graduated down to 0001 for precise hole placement. Knee mill, a knee and collar mill refers to any milling machine whose XY table rides up and down the column on a vertically adjustable knee. This includes Bridgeports. Planer-style mill, large mills built in the same configuration as planers except with a milling spindle instead of a planing head. This term is growing dated as planers themselves are largely a thing of the past. Ram-type mill, this can refer to any mill that has a cutting head mounted on a sliding ram. The spindle can be oriented either vertically or horizontally. In practice, most mills with rams also involve swiveling ability, whether or not it is called turret mounting. The Bridgeport configuration can be classified as a vertical head ram-type mill. Van Norman specialized in ram-type mills through most of the 20th century. Since the wide dissemination of CNC machines, ram-type mills are still made in the Bridgeport configuration, but the less common variations have died out, the work being done there by either Bridgeport firm mills or machining centers. Turret mill, more commonly referred to as Bridgeport-type milling machines. The spindle can be aligned in many different positions for a very versatile, if somewhat less rigid machine. Alternative terminology. A milling machine is often called a mill by machinists. The archaic term miller was commonly used in the 19th and early 20th centuries. Since the 1960s there has developed an overlap of usage between the terms milling machine and machining center. CNC machining centers evolved from milling machines, which is why the terminology evolved gradually with considerable overlap that still persists. The distinction, when one is made, is that a machining center is a mill with features that pre-CNC mills never had, especially an automatic tool changer that includes a tool magazine, and sometimes an automatic pallet changer. In typical usage, all machining centers are mills, but not all mills are machining centers. Only mills with ATCs are machining centers. Computer numerical control. Most CNC milling machines are computer-controlled vertical mills with the ability to move the spindle vertically along the Z-axis. This extra degree of freedom permits the use in desinking, engraving applications, and 2.5D surfaces such as relief sculptures. When combined with the use of conical tools or a bull-nose cutter, it also significantly improves milling precision without impacting speed, providing a cost-efficient alternative to most flat-surface hand engraving work. CNC machines can exist in virtually any of the forms of manual machinery, like horizontal mills. The most advanced CNC milling machines, the multi-axis machine, add 2 more axes in addition to the 3 normal axes. Horizontal milling machines also have a CEQ axis, allowing the horizontally mounted workpiece to be rotated, essentially allowing asymmetric and eccentric turning. The 5th axis controls the tilt of the tool itself. When all of these axes are used in conjunction with each other, extremely complicated geometries, even organic geometries such as a human head, can be made with relative ease with these machines. But the skill to program such geometries is beyond that of most operators. Therefore, 5-axis milling machines are practically always programmed with CAM. The operating system of such machines is a closed-loop system and functions on feedback. These machines have developed from the basic NC machines. A computerized form of NC machines is known as CNC machines. A set of instructions is used to guide the machine for desired operations. Some very commonly used codes, which are used in the program, are G00 Rapid Traverse, G01 Linear Interpolation of Tool, G21 Dimensions in Metric Units, M03, M04 Spindle Start, M30 Program End. Various other codes are also used. A CNC machine is operated by a single operator called a programmer. This machine is capable of performing various operations automatically and economically. With the declining price of computers and open-source CNC software, the entry price of CNC machines has plummeted. Tooling. The accessories and cutting tools used on machine tools are referred to in aggregate by the mass noun tooling. There is a high degree of standardization of the tooling used with CNC milling machines, and a lesser degree with manual milling machines. To ease up the organization of the tooling in CNC production, many companies use a tool management solution. Milling cutters for specific applications are held in various tooling configurations. CNC milling machines nearly always use SK, cut BT or HSK tooling. SK tooling is the most common in Europe, while CAT tooling, sometimes called V-flange tooling, is the oldest and probably most common type in the USA. CAT tooling was invented by Caterpillar Inc. of Peoria, Illinois, in order to standardize the tooling used on the machinery. CAT tooling comes in a range of sizes designated as CAT 30, CAT 40, CAT 50, etc. The number refers to the Association for Manufacturing Technology taper size of the tool. An improvement on CAT tooling is BT tooling, which looks similar and can easily be confused with CAT tooling. Like CAT tooling, BT tooling comes in a range of sizes and uses the same NMTB body taper. However, BT tooling is symmetrical about the spindle axis, which CAT tooling is not. This gives BT tooling greater stability and balance at high speeds. One other subtle difference between these two tool holders is the thread used to hold the pull stud. CAT tooling is all imperial thread and BT tooling is all metric thread. Note that this affects the pull stud only, it does not affect the tool that they can hold. Both types of tooling are sold to accept both imperial and metric size tools. SK and HSK tooling, sometimes called Holoshang tooling, is much more common in Europe where it was invented than it is in the United States. It is claimed that HSK tooling is even better than BT tooling at high speeds. The holding mechanism for HSK tooling is placed within the body of the tool, and as spindle speed increases, it expands, gripping the tool more tightly with increasing spindle speed. There is no pull stud with this type of tooling. For manual milling machines, there is less standardization, because a greater plurality of formerly competing standards exist. Newer and larger manual machines usually use NMTB tooling. This tooling is somewhat similar to CAT tooling but requires a drawbar within the milling machine. Furthermore, there are a number of variations with NMTB tooling that make interchangeability troublesome. The older a machine, the greater the plurality of standards that may apply. However, two standards that have seen especially wide usage of the Morse number 2 and the R8, whose prevalence was driven by the popularity of the mills built by Bridgeport Machines of Bridgeport, Connecticut. These mills dominated the market for such a long time that Bridgeport is virtually synonymous with manual milling machine. Most of the machines that Bridgeport made between 1938 and 1965 used a Morse taper number 2, and from about 1965 onward most used an R8 taper. Accessories: arbor support, stop block,